Watching this video will probably not help you learn any chemistry. Watching is not the same thing as thinking. You want to learn from this video, it's going to be a lot more beneficial if it is done interactively. Try to answer the questions that are posed along the way. If you simply follow along, you might be able to get some of the ideas, but it won't be the same thing as if you think about them more deeply. Trust me, there are more amusing videos on the internet than this one. The topics within this video come from Chapter 1 of our textbook. They involve making and reporting measurements and include things like unit conversions, significant figures, and performing scale readings. So for reporting measurements, let's start with an actual problem. What is the width of this object? Well, we need a measuring device. Let's say we have a meter stick. With a meter stick, we could record and report the value at 0.50 centimeters. How do we get this value? If we zoom in, we can see that one end of the mark is placed at the 2 centimeter mark. The other end sure looks like it's right at the 2.5 centimeter mark. If the position was a little above 2.5, we wouldn't call it 2.5. We might estimate it as 2.51 or 2.52 centimeters, but this one sure looks to be right on the 2.5 mark. So in this case, we could estimate the left and right values as 2.00 and 2.50 centimeters. Using the meter stick, if we take the difference of those, the best that we could report would be 0.50 centimeters for the width of this object. What if we used a different measuring device? Here we see the same blue, whatever we want to call it, being measured with a set of digital calipers. With the digital calipers, the width is reported at 5.00 millimeters. All of the digits that are being shown on the output, the 5.00, are measured and reported. Is this the same as 0.50 centimeters? Well, let's see. If we convert from millimeters to centimeters, we can compare. So 5.00 millimeters, the units to convert between those, our metric conversion would be 1 centimeter is 10 millimeters. That's a precise, exact relationship. And so if we do a little dimensional analysis, we see that 5.00 millimeters would be 0.500 centimeters. So with the calipers, we have a more precise reading. With the calipers, we can report the value to 3 decimal places using centimeters. With the meter stick, we could only report the value to 2 decimal places. So oftentimes, our measuring device will give us a different precision or a different certainty within our measurement that we make. So if we're able to measure it and get to 0.500 centimeters with the digital calipers, we want to report it that way. So we let whoever we're communicating with know how precisely we have measured the object or whatever we're seeking to measure in the first place. This idea of reporting values as carefully as we can, where we express the certainty or uncertainty within the measurement, that leads us to the idea of significant figures. We have various rules or guidelines when we're identifying significant figures. But really they come down to the point that when we have a number, it's significant. However, we have a question when it comes to zeros, because within our numbering system, sometimes the zeros are used simply to hold the place for the different measured digits, and sometimes we've actually measured them. With this number here, 2,000, how would we report the number of significant figures in that? What are the zeros really doing? Well, if it's just written as 2,000, there's only one significant digit, that leading 2. The other ones are simply used to hold the place and to indicate that the 2 is in the thousandths place. So it would actually be representing the value of 2,000 plus or minus 1,000, where there's plus or minus 1 uncertainty in the digit that we're reporting as being significant. So if the 2,000 only has one significant figure with our guidelines here, take a second, pause the video, see if you can determine the number of significant figures in these other examples right here, and then we'll compare our answers. Okay, here are my answers. If you paused the video and worked it through, my hunch is that you agree with many of these. Most of the times when I discuss this with my students, the main one that they're uncertain on is this value right here. How does it have three significant figures? Shouldn't it only be two, the 1 and the 5? Well, we have that trailing 0 at the end. Why do we report that at all? Well, it's not holding the place for anything. We didn't need to include it unless we were certain of its particular magnitude. We write it there because we've somehow had it measured with the device that we were using. Now, it's one thing to be able to identify the number of significant figures that we have, but most of the time we're going to be using them in calculations. We want to be very clear that there are different sets of rules when we're adding or subtracting numbers versus multiplying or dividing them. Oftentimes students confuse these and use the multiplication or division rule every time, and they forget to use the addition or subtraction rule properly. Let's first look at the addition or subtraction rule. Here we have an addition problem. It's shown where all of the digits that are spit out from the calculator are shown. But how would we determine the number of significant figures? The rule for addition or subtraction is that the answers are rounded to the least significant decimal place. What does this mean in practical terms? With addition or subtraction, it's always a good idea to stack the numbers one on top of the other. Stack them up so the places match up. The ones place over the ones place, the tens over the tens, etc. Notice that in the 312,520, the 2 is the last significant number. The 0 at the end is simply holding the place for it. How do I know? Well, if that 0 was significant, I could show it was significant in one of two ways. I could include a decimal point that would show that that 0 had been significant. Or probably the best approach would be simply to write it in scientific notation, where within scientific notation, all of the significant digits are shown. However, in this case, the 0 at the end is not significant. So in the 312,520, that value is only significant to the tens place. So then when I do the operation and add it together, my final answer can only be reported as being significant to the tens place as well. I see once again that if I have that 0 at the end, it's going to be best to express the answer probably in scientific notation. I have different rules when I'm doing multiplication or division. In this case, the least number of significant figures in either of the numbers that I'm dealing with will dictate how many significant I have in the final answer. So if I've got 32.50 being multiplied by 64,300, first of all, identify how many significant figures are in each of those, and then determine how many should be in your answer. Pause the video and see what you think. Well, the first has 4 significant figures, and the second 3 significant figures. So when I take what the calculator spit out for me, I would find that the final answer should have 3 significant figures. That would be most easily expressed in scientific notation. Now, however, oftentimes we would do a calculation, then we'll use it in a subsequent step. If we're using it in a subsequent step, it's not a good idea to round at every step along the way. Instead, we should round at the end. So if we wanted to take this same value, not round it, but indicate to ourselves the number of significant figures that we have, oftentimes it's a good practice to underline the last significant figure that we have. So in this case, we had 3 significant figures, so the 2, the 0, and the 8 were all significant. Putting an underline under the 8 could help us remember what the last significant place was. So when we have our rules for doing calculations involving significant figures, remember there's different rules for addition and subtraction versus multiplication and division. Oftentimes when we have multiple steps, we're not going to round until the final step. One other idea is that some numbers we will call exact. These will not affect the number of significant figures. An exact number is either something that we can define or have it be exactly counted. That will not affect the number of significant figures in our overall calculation. So what would be an example of an exact number versus an inexact number? Significant figures are measuring the uncertainty in the quantities that we measure. So when would we not have uncertainty in the quantity that we measure? It could be an exact number, or it could be something that's, well, an exact number, which means it's either defined or exactly counted. So take a second. Look at the choices here. Which of these, if any, would represent an exact number? Meaning we could precisely know its value. See what you think. Okay, so within this one, the number of people in Ohio, well, first of all, you might think you can't have a fractional person, but exactly how would you determine that? Would you do some kind of polling? How would you possibly come up with that value? I think you'd have to measure it in some way. So there's going to be some uncertainty regarding the number of people in Ohio at any one moment. The mass of a golf ball, the density of a golf ball, these are both things that you'd have to measure. So A, B, and C, I would say that they are all inexact numbers. The number of grams in a kilogram, however, that's something that's defined. There is not any variability in that. So when you look at that as a conversion factor, in a sense, it has an infinite number of significant figures for us. Okay, let's combine these ideas and look at a few exam questions. Almost all the time on the exam, when it comes to testing the idea of significant figures, it's what would be a mixed operation calculation. So you have one portion being addition and subtraction, another portion being multiplication or division. That's what we see here. Take a second, pause the video, see if you can come up with an answer for this one. Okay, since this is a mixed operation, the first thing I would do is see that, okay, I have to do addition or subtraction. If it's addition or subtraction, I'm definitely going to stack it up. I put them one over the top of each other in terms of lining up the decimal points in the places. When I do this, I see that I'm limited by the fact that 42.70 only goes to two decimal points, two decimal places. So my final answer can also only go to two decimal places. That's applying the rules for addition. Once again, I don't want to round at this point, so I'm going to designate that the value there is significant to 42.95 where the 5 is being underlined. But I'm going to take the whole value and use it in the next step of the calculation, which is the division portion. So within this one, we have to identify the number of significant figures in the numerator and the denominator, which is 4 and 6 respectively. I can do the math within that. I calculate it and I find that the final answer should have 4 significant figures. Once again, I didn't round after the addition and subtraction stage. Also, I had two different sets of rules. Remember, for the addition and subtraction, I stacked them up. And for the division, in this case, I ended up identifying the number of significant figures in either of them, and that's what guided my answer. Okay, here's another mixed operation one from a test that we had before. Pause the video, see if you can figure out this one. Okay, this one's a little bit different. It's asking to say how many significant figures. It's not asking for a specific value. As I look at it, I see that I have a subtraction and I have an addition in the numerator that I'm going to have to do first. Those are both examples where I'm going to stack up the parts in order to do the calculation. So when I stack them up based on place, I can determine to what digit in each case it's going to be significant. I don't want to round it at this point, but I'm going to underline it so I know the values that I have. And I know to what point they're being significant. Next, we can do the multiplication. 86.23 has 4 significant figures. 138.8231 was only significant to the 8 in the ones place. So the final answer is going to have 3 significant figures. The next step is to take that value and divide it by 6. Now 6 is said to be an exact number. So if I had 3 significant figures before that, I'm going to have 3 significant figures after that. So this is a calculation that's best reported then to 3 significant figures. Okay, let's try this one. We're going to see what is the mass of a magnesium block that measures 2.5 centimeters, 3.5 centimeters by 1.5 centimeters. And we have the density. Now in all of these, it looks like we have some examples that are reported to 3 significant figures, and most of them are reported to 2 significant figures. But I suppose the main question here is we have to figure out what is the mass of that block. To do that, we're going to have to be able to convert between volumes where we're going to have centimeter times centimeter times centimeter, which is cubic centimeters, and somehow get that into liters. Well, by definition, we need to know that 1 cubic centimeter is 1 milliliter and that there's 1,000 milliliters in 1 liter. Both of these would be pieces of information that I would not expect to be provided on the test. It's going to be something that you're going to have to know. So the volume of this block right here, if we work it through, is going to be 13.125 cubic centimeters, which is the same as 13.125 milliliters, and it's going to have 2 significant figures in it. We now can convert that into a mass. 13.125 mils, well, we know that for every 1 liter there's 1,000 milliliters. That's an exact relationship. And the density is given that there's 1.738 kilograms for every liter that we have. So now we've gone through and we've calculated the mass in kilograms. Now if I look at this though, I only see one choice where the mass is in kilograms, and the other ones are involving grams and milligrams. So this question is really combining multiple ideas. It's combining, in one respect, significant figures, but it's certainly combining being able to do volume conversions. And now it looks like it's asking, can I do metric conversions between kilograms and things like grams and milligrams? Let's give that a try. So to convert between kilograms and milligrams, I have an exact relationship where 1 kilogram was 1,000 grams, and then finally 1 gram was 1,000 milligrams. So this block right here that's 0.023 kilograms would be 23,000 milligrams. That wasn't one of the answers. What happens if I convert it to grams? 0.023 kilograms. The exact relationship was 1 kilogram was 1,000 grams. That leads me to say that the block is 23 grams for its mass. Yep, that's one of the choices. So within this one, notice there are several ideas. We have to be able to convert between volume and then do some dimensional analysis and know conversion factors between things like grams, kilograms, and milligrams. Now, the unit volume as cubic centimeters, one other way you might see it would be to express it in a different set of cubic units, like let's say cubic meters. How would we do that? Well, by definition, 1 meter is 100 centimeters. When we set up our unit conversion now, if we had 13 cubic centimeters, for example, it's not a conversion simply between 1 meter and 100 centimeters because we needed to get to cubic centimeters. So we'd take the 1 meter, cube that whole term, the 100 centimeters, cube that whole term, which is 100 times 100 times 100. This is how we end up doing a volume conversion involving cubic units. This is a good thing to give a little bit of practice to. So you might want to pause the video and see if this part makes sense to you. Another thing when it comes to reading measurements is how do we handle a scale reading? That's what this question's about. We see 4 different containers, each holding different amounts of a particular liquid. And they also have different markings on them. So the question is, which of these volume reading is reported with the most significant figures? I look at that first one, I would report its value at about 20.38. I'm going to read from the bottom of the meniscus, and it appears to be a little less, a little before that 20.4 mark. So I'd estimate it as 20.38. Notice within case 1 there, the numbers are smaller at the top and they increase as you go down. The burette you use in lab is going to be similar to that. Take a second now, reading from the bottom of the meniscus, how would you report the readings for the containers 2, 3, and 4? Pause the video and see which of these has the most significant figures. These are the different values that I would have. In case 2, 63.4, case 3, 38.0, and case 4, 6.59. In each case, I'm going to read the number of digits that I can clearly see and then estimate the last one. So the one with the most significant figures would be the 20.38, which has 4 significant figures. All of the other ones have 3 significant figures. Okay, here's another way that we can look at the same scale readings. So all of these are the volume readings in milliliters, but now it asks which is reported with the greatest precision. Which of these do we know most certainly? In this case, I'm going to look at to see, since they're all in milliliters, which one is being reported to the greatest number of decimal points, the largest number of decimal points. That's the most precise reading. It looks like in cases both 1 and 4, based on the markings, I'm able to report them to 2 decimal places. It looks like numbers 2 and 3, I can only report to 1 decimal point. So both 1 and 4 are reported with the same greatest precision. Both of these are measured to the 0.01 milliliter mark. So they are the most precise. So the topics that we covered here involve making and reporting measurements. They include a little bit of unit conversions, the idea of significant figures, especially in mixed operation calculations and performing scale readings. If you haven't mastered these, you definitely need more practice. Once again, these ideas won't appear on your exam, so it's definitely important to take away the ideas so you get the questions right on the exam. If you made some mistakes, good. Make sure you document and improve from there. The most difficult topic typically I would find here on the test is that mixed operation significant figures question. Give that one another try and try more examples from the end of your book if you want to reach mastery.